So, this is the first lecture of week 12. This is the final week of this course. In the past 11 weeks, we have learnt extensively about many algorithms in both unconstrained optimization as well as constrained optimization. And in constrained optimization, we learnt in detail about certain algorithms for nonlinear programming and certain algorithms for linear programming as well, right. So, yeah, if you recall, we had gradient descent, conjugate gradient algorithm, Newton's method, quasi-Newton's method, all of these for unconstrained optimization. In constrained optimization, we for nonlinear program we discussed about the penalty method, right, and the augmented Lagrangian method. In linear programming, we discussed about simplex method, affine scaling, and Karmaker's algorithm. Okay, so quite a lot of methods, right. Possibly one of the basic questions that we have not addressed much is the question that where are these algorithms actually used, right. So, of course, if you want to solve an optimization problem, yeah, in many industries people have optimization problems to solve, and I mean you just type these values and give it to a computer, the computer gives you the answer, right. That is fine, not a problem. In the whole of this week, right, I wanted to actually take up a particular application, okay, and specifically in machine learning, because I mean that is one of the things that is being used very extensively, right. So, and discuss the role of optimization algorithms in machine learning. Okay. Plan is as follows. So, we will I will first explain the application in a little bit of detail, because I want you to understand what the application is, right. So, I will start from the basics of machine learning, okay, a little fast. I will explain what I mean machine learning is, give some examples, and converge on a particular technique, a particular method in machine learning, and then discuss how the optimization algorithms that we have learnt in the past 11 weeks are going to be useful in yeah, finding the solution of this particular method in machine learning. Okay. We will also take a data set that is publicly available. Okay. So, I will start with what is machine learning. Okay. I mean maybe many of you know this, but I mean since at least some of you would like to know an outline, I will just go fast on what machine learning is. Okay. So, let me start with an example. Okay. So, consider the problem of finding whether a given mail is spam or not spam, right. So, that is something the machine finds out by itself, right. So, many of you are using Gmail or yeah, other popular mail servers, right. So, if you actually get a mail, right, the Gmail itself decides whether the particular mail is spam or not, right, with near 100% accuracy, right. Yeah, maybe it is 99.5 or something, but it is okay. I mean when you get 100 mails or 1000 mails, about 995 or 999 is classified correctly, and only maybe 1 or 2 yeah, is wrongly classified as yeah, if a spam mail is classified as not spam and not spam is classified as spam, right. How did this happen? I mean how does the machine know by itself that a mail is spam or not, right. So, yeah, if you are familiar with machine learning, you might have known that machine learning is used in this problem, right. So, this problem is actually called as the spam detection problem. Okay. So, these are some examples of machine learning. Okay. So, what is spam detection problem? It is I mean to put it in simple words. Okay. When you are given a mail, right. So, this is a task, right. When you are given an email, classify it either as spam or not spam. Okay. So, fine, that is the task, but I mean how would you make a computer do this, right. The simple answer for that question is that ask this question instead of a computer. Suppose you have a child, okay. So, let us say someone who is in his first standard or something, okay, a 5-year-old or a 6-year-old kid, okay. How will you teach him about this? So, I mean he possibly does not know about computers, or he knows very little bit, he knows what is email and something of that sort. Let us assume that way, okay. How would you teach him to seeing a mail whether it is a spam or not spam, right. So, I mean if you think of this, at least I would do the following. I will give him many examples, right. So, I will just show, okay, a particular email saying that, see, this is how a spam looks, right. So, maybe there is a message which says so you get $2 million, right. So, this is possibly a spam mail, right. And then I show him some normal mails which are not spam, right. So, the kid sees hundreds of mails like this, thousands of mail like this, okay. Eventually the next mail that comes, right. So, when the next mail comes, he will not need my help, right. So, he will just see that the mail is okay. So, this is just a spam mail, because when you see something like this, as I said, $2 million or something, right. So, he will immediately say it's spam, otherwise he says, yeah, it's a normal mail, it's not a spam, right. So, what has actually happened? You have actually given some labeled data. What is labeled data? There is data and then there is a label. The data is the email and the label is whether it is a spam or not spam, right. You gave many examples of spam, many examples of not spam mails. What did the child do? He saw many such mails, and based on that he actually learnt whether a new mail that comes is a spam or not, right. We are exactly going to do the same to a computer, okay. We are going to give many labeled data. We are going to give the mails, okay, initially with a label, okay. So, we are going to say that, yeah, particular mails are spam, particular mails are not spam, right. So, I mean to put it in mathematical terms, right. So, you are giving something called as data points, okay. So, assume that, so what is the data? So, yeah, you give email 1. So, in this problem, okay, you give them email 1 and then also give a label 1. So, label 1 could be spam or not spam, okay. So, then you give email 2, then you have a label 2 which is possibly spam or not spam, right. So, maybe some n emails, thousands of emails maybe, Okay. Again this says spam or not spam. Okay. So, what you have actually given here, okay, is what we call as the data set. Okay. So, data set consists of n data points. Okay. So, we usually write it this way in general. Okay. So, yeah, in general, so this is for a spam detection problem. Okay. So, in general, for any supervised learning problem, okay, you will have a data set, okay, where you are given some labeled data. Okay. What are these data? X1, Y1 is like email 1 and label 1. Okay. So, X1 is, it could be large, right. So, it has I mean it's like a vector, for example. Okay. So, here it is the vector of words. Okay. So, I mean so if you cannot directly compare this, right. So, X1 is yeah, in any Xi for that matter, right. So, Xi will be a vector which belongs to RP, okay, and Yi yeah, so based on the problem, okay. So, I mean I am considering a certain kind of a problem where yi could belong to a real number, okay. So, here it is not even that, here it is actually I mean 0 or 1, right. So, it is because what I have given in an example is called as a classification problem, right. So, you either classify it as 0 or 1, but yeah, we could have a regression problem, okay. So, that is called as the categorical data, okay. So, where the label could actually be a real number, okay. So, yeah, this is what you have as a data, right. You have n data points where xi belongs to rp and yi belongs to r, okay. Yeah, it need not be r, it could be say yeah, a bunch of a1, a2 dot 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 ak also. So, if it is this, it is a regression problem. If it is this, it is a classification problem. Right. So, yeah, the spam detection problem is a classification problem. If you have a regression problem, so regression problem for example is, let us say the stock market prediction problem. Okay. In that you will have so the problem is based on the previous data you have to predict the stocks of the following days. Okay. So, suppose I give you the Sensex data, okay, for the last few years, okay, with many other parameters, not just the Sensex data. Let us say about, let us say how many companies are trading, how many people are investing, and yeah, the macro details like the GDP growth and so on. Okay. So, let us say you are given all these data points on a daily basis and the stock value. Okay. So, you will have to predict what is going to be the stock the next day. Okay. So, that is like the stock market prediction problem, and here you are actually having a labeled data because for the set of features, that is for the number of people trading, the economic condition and so on, right. So, these are the set of features that you have on the left, right, that these are the set of independent variables, right, and on the right you have a dependent variable which is the stock market price, right. So, and the stock market price is not like 0 or 1, right. So, it could be any number, any real number, right. So, yeah, that is a kind of a problem where it is actually a regression problem and not a classification problem, right. Okay. So, this is the data that is given to you. Okay. From this, the task that you have is, okay, given a test vector x naught, okay, find y naught. Okay. So, I have told you that when the vector is x1 the label is y1, when the vector is x2 the label is y2 dot dot dot, when the vector is xn the label is yn. Okay. Now, I am going to give a very completely new vector x naught, and I am going to ask you to find y naught. Okay. So, that is actually the task. Okay. But how will you find that? I mean, this seems to be a very superficial problem, right. Of course, I mean, yeah, you have an example of this spam detection problem where yeah, you were given email 1 which is x1 and y1 which is spam or not spam. Similarly, you were given up to xn up to and the label yn again which is spam or not spam. Now, you are given a new x naught which is a new email, and you are asked to classify whether it is spam or not spam, right. So, in a similar way, if it is stock market prediction, you have a set of features, right, for which you were given the stock price for hundreds of days or thousands of days. Okay. And on a new day, you are having the set of parameters now, you are going to predict what is y naught. Okay. So, how do you do this? I mean, this seems to be again a very superficial problem, right. What you do is you assume that y and x are related as related in the form of a function. Okay. So, assume that y and x are related as y equal to f of x. Okay. So, the task is now to find little f. Okay. So, yeah, so maybe the revised task I will say. Okay. The revised task is given x naught, okay, find or estimate, rather I will write it this way. Yeah, so this is a better way. Estimate f in such a way that, okay, for a given test vector x naught, okay, f of x naught and f hat of x naught is close enough. Okay. Again, close enough I have to write it in quotes, right, because I have not mentioned what close enough means or how close is close, right. So, all that I have not mentioned. Okay. So, again to refine this statement to say what does close enough mean. Okay. What I am going to do is I am going to define something called as a loss function. Okay. Define a loss function f which is actually from y cross y, sorry L because it is loss, right. So, I will write L which is the space from which y is taken. Okay. So, yeah, a better way to write this is actually xi in x which is a subset of Rp, okay, and yi is in some y which is a subset of R, okay, or a subset of this. Okay. Fine. Nevertheless, okay. So, yeah, if you are asking how the loss function is, okay, so there are some popular loss functions. Okay. For example, squared loss is of this form. Okay. Squared loss means L of y comma y hat is just norm y minus y hat the whole squared. Okay. Absolute loss is the absolute value of y minus y hat. Okay. Fine. And so, yeah, these are used for regressions in general. okay. And yeah, so you also have the 0 1 loss, which is 0 if y equal to y hat and 1 if y not equal to y hat, okay. So this is usually used for classification problems. So that is, if you classify spam as spam, the loss is 0. If you classify spam as not spam, then it is 1, or not spam as spam, it is 1, okay. If you classify not spam as not spam, the loss is 0, okay. So yeah, these are some nice loss functions. You can have many other loss functions as well, okay. Yeah, now I have defined a loss function. I will revise the task again, okay. Further revised, I will write it if you want. Okay. So yeah, given a test vector x naught, estimate f hat of x naught such that L of f of x naught comma f hat of x naught is minimized, okay. So this is basically what you need to find, okay. So if you are following it closely until now, you might have actually seen that we have got an optimization problem, right. So you are actually finding a function f, okay. So yeah, here it is an estimation problem, so it is f hat, okay. So you are finding f hat in such a way that the loss function L of f of x naught comma f hat of x naught should be minimized, right. So roughly you can see that this is actually an optimization problem, right, because in an optimization problem what do you do? You are actually minimizing some function of some variables, okay, possibly subject to some constraints or subject to no constraints, right. So L of f of x naught comma f hat of x naught is a function of f hat, right, and you are minimizing this with respect to f hat, right. So in very general terms, okay, any supervised learning problem. So in this I have not pinpointed a particular supervised learning problem, right. So any supervised learning problem is of this form. So you have a labeled data, right, x1 y1 dot x and yn, right. You assume that there is a relation y equal to f of x, right, and yeah, given a test vector x naught, your task is to minimize L of f of x naught comma f hat of x naught for some given loss function L, right. So this is the general structure for any supervised learning problem, and you can see that any supervised learning problem has an optimization problem embedded within itself, okay. So if you want to work out, if you want to find f hat that minimizes this loss function, you have to solve an optimization problem, and to solve an optimization problem you have to use optimization algorithms, okay. So and that is the reason why you actually want optimization algorithms in the first place, okay, fine. So I will further speak about the functions now, okay. Let us say this problem whatever I have mentioned here, right. So we assume that y and x are related as y equal to f of x, right. So but if you consider any general function f, okay, so it is very hard, okay, to solve such a problem, right. So what we do is we actually assume that for different methods, okay, so we make some simplifying assumptions on this function f, okay. So I am not sure how many of you have heard of this popular method called OLS, it is called ordinary least squares, okay, or in general a linear regression or linear classification problems, okay. So what does this OLS method do? OLS method actually assumes f to be linear in x, Okay. So, instead of assuming any general function f, okay, so it assumes that f is actually linear, okay, and then solves just for the coefficients of the linear function. Okay. So, not just OLS, OLS is the most popular method which assumes f to be linear. Okay. The simplifying assumption is that the function that relates y and x is a linear function. Okay. There are other methods like ridge regression, lasso, and there are a few other shrinkage methods as well. I mean those are popular. Okay. So, yeah, I mean maybe I will just write that down. Okay. In general, we have some simplifying assumptions on f. Okay. So, I mean there are methods which does not have this, but yeah, many of the methods have such simplifying assumptions. Okay. So, to cite a few, okay. So, the methods what I just said for now, okay, OLS, which is ordinary least squares, right, ridge regression, assume that f is linear, okay, and yeah, so you might see this as CART, which is classification and regression trees, okay. Or it is also called decision trees. Okay. I mean these are different names of the same method. Okay. So, this assumes that f is a constant in axis parallel okay. So, yeah, and I can cite many such examples as well. Okay. So, let me explain, give a primer on what does this simplifying assumption mean, right. If f is linear, okay, then we have y is beta naught plus beta 1 x 1 plus beta 2 x 2 plus dot 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 plus beta p x p, where x is the vector x 1 x 2 dot 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 x p. Okay. So, please recall that x I is, I mean each of these x I, x 1 x 2 dot 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 x n, right. So, each of this is a subset of R p, that means it has a p dimensional vector, right. So, each of the example that you will consider will have a p dimensional vector, right. So, if y is linear in x, that means yeah, it has to be of this form, where yeah, you have a constant plus beta 1 into the first element of the vector plus beta 2 into the second element of the vector plus dot 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 beta p into the pth element of the vector. Okay. And if the loss is squared loss, okay, if loss is squared loss, then yeah, we need to minimize. Okay. So, yeah, f of x naught. So, L of f of x naught comma f hat of x naught, right, is norm of f of x naught minus f hat of x naught the whole squared, right. But f of x naught is beta naught plus beta 1 x 1 plus beta 2 x 2 plus dot 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 plus beta p x p, right. So, yeah, in f you will have beta naught beta 1 dot dot beta p, and in f hat you will have beta naught hat dot 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 beta p hat, right. So, yeah, this is just going to be, so yeah, f of x naught is y, right. So, it is y minus beta naught hat minus summation beta I hat x I equal to 1 to p the whole square. Okay. So, this is the quantity that we have to minimize. Okay. So, now we have a very nice optimization problem to look at, right. You want to minimize some mathematical quantity which I have nicely defined, right. So, this actually gives you a nice example of how optimization problems can be used to solve certain machine learning applications. Okay. So, we will actually continue in the next lecture on this same example where we have the simplifying assumption that f is linear. Okay. And we will actually discuss different methods before we converge to the method that we are looking for. Okay. Thank you.